Welcome. It's a pleasure to welcome today Tamara Broderick. Tamara has gotten her undergraduate from Princeton. After that, she went on to University of Cambridge under a Marshall Scholarship, where she followed on to a PhD at UC Berkeley, working with Mike Jordan under an NSF fellowship. She's been doing some exciting work in Bayesian non-parametrics over the last several years, and today she's going to share some of those results with us. Thank you very much for joining us.
Oh, thank you. I hope you'll bear with me. I'm losing my voice a little bit due to a cold. But today I'll be talking about feature allocations, which I'll start by defining as an extension of clustering. I'll talk about how we can characterize feature allocations, distributions over feature allocations, using things called probability functions and paintboxes. And finally, I'll talk about how we can learn different types of latent structure in data, including feature allocations, and what's the sort of inference that we can do there. So let's start with feature allocations. So in general in this talk, I'm going to be concerned with unsupervised learning. So the case where we have a bunch of data, it's unlabeled, and we want to find meaningful latent structure in that data. And sort of the canonical example of that problem is clustering, where we want to assign each data point to one and only one group called a cluster. Now, again, we want this latent structure to be meaningful. So we might be very pleased to find, for instance, suppose our data set is a collection of pictures, and we've clustered them. And after the fact, we find that one of our clusters contains pictures of cats, one contains pictures of dogs, et cetera. Now, another way that we can represent this belonging is in the following form. So here I'm basically saying that pictures 1, 2, and 7 belong to a cluster together. Pictures 3 and 5 belong to a cluster. Picture 4 belongs to a cluster. And something I want to emphasize about this is that I'm sort of showing this as a matrix, but this isn't really a matrix. There's no ordering on the columns here because we don't know these groups in advance. We don't know what they mean. That's part of the problem, that we're trying to find those things. But what is nice about this representation is I think that you can see that sometimes clustering falls short in terms of what we want to find. I mean, what if, for instance, I have a picture in this toy example of a cat and a dog, or a cat and a dog and a mouse, or no animals are in my picture? Then clustering is sort of the wrong representation for this, and I actually want my data points to be able to belong to multiple groups, or no groups, or one group is fine. And in this case, instead of a clustering, we have a feature allocation, and instead of the groups being called clusters, we call them features. And so again, there are sort of two parts to my talk. So the first part is going to be about characterizing distributions over these types of combinatorial structures. And so in particular, what types of distributions can we have over these so-called feature allocations, this extension of clustering? And I'm going to make just two very weak assumptions about those distributions. One, that they're exchangeable. So what I mean by exchangeable is that if I saw the data points in a different order, it wouldn't matter. If I happen to see picture 6 before picture 1, it wouldn't change the distribution. And two, I'm going to assume that there's a finite number of features per data point. So let me be clear about this. I don't mean that there's some fixed bound on the number of features. I'm not saying that I know the number of features in advance. What I'm saying is that any particular data point can exhibit some potentially unbounded number of features, but that number is finite. And so this is just sort of common sense. So for instance, again, in this toy example, I have a finite number of pixels. I don't expect to see more than one animal per pixel. So just a very common sense assumption. OK, so let's say that we make these two simple assumptions. Then what can we say about distributions over exchangeable feature allocations? Well, just as sort of inspiration, I'll note that the exchangeable clusterings are very well characterized. There's sort of a number of representations that are known for the distributions over exchangeable clusterings. And sort of the tack that I'm going to take today is to say, well, we know things about exchangeable cluster distributions. Let's review those and maybe try to find out what we can say about exchangeable feature distributions given that knowledge. So to start out, let's just say, OK, well, what can I say about the probability of some clustering if I know that it's exchangeable? So here, let's say I just have some particular instantiation of my clustering. It has n data points that I'm clustering. So that's the number of rows. And suppose those data points happen to belong to k clusters in this particular instantiation. Then what can I say about the probability of this clustering? Well, in general, if I have an exchangeable clustering, then I can always express the probability of that clustering as some symmetric function p of the sizes of the clusters. So the size of a particular cluster is the number of data points that belong to that cluster. So here, for instance, there are 3 data points in the first cluster. There's 1 data point in the kth cluster. And again, there's no ordering on these clusters, so it's a symmetric function. Now, when this function exists, which again it always does for exchangeable cluster distributions, it's called the Exchangeable Partition Probability Function, or EPPF. And so a very natural question is, well, is there something similar for exchangeable feature allocations? Maybe I can always express the probability of some exchangeable feature allocation as some symmetric function of the sizes of the features. So we want to know, does this EFPF that I'm just sort of proposing right now, does that exist? Now, to get at that question, let me introduce you to a particular example of an exchangeable feature allocation. It's called the Indian buffet process, and it works like follows. So we're going to fill in our exchangeable feature allocation by examining each data point one at a time. And for each data point, we're going to do the following. We're going to say that, number 1, the data point has features that we've seen before with probability proportional to the number of times that feature has occurred. That's this Sn minus 1k. Here, theta is just some parameter of the model, and n is the number of data points that we've seen so far. Next, we're going to say that a data point has a Poisson-distributed number of new features. So here, gamma is just some other parameter of the model. So what does this look like when we're filling in our exchangeable feature allocation? Well, on the first data point, we haven't seen any features so far, so we skip the first step. We go to the second step, generate a Poisson number of features, and maybe that Poisson number happens to be 2. For the next data point, we've seen 2 features so far. So for n equals 2, we go to step 1 and say, OK, we're going to make a Bernoulli draw for each of these features. Maybe we have one feature and not the other. And then we're going to draw a Poisson number of new features, and maybe that number just happens to be 0 this time. And then we'll just keep doing this to fill in the remaining feature assignments of each of the data points. And now that we have this sort of generative model here, we can calculate what's the probability of some particular feature allocation that we generated this way. And I'll tell you the answer. These gamma functions essentially come from the Bernoulli draws. This exponential comes from the Poisson. But really, remember, the form of this equation is what's important. Does it look like an exchangeable partition probability function, but in some sort of feature way? In particular, we notice that it's a function of the sizes of the k features, just like the EPPF, the partition version, was a function of the sizes of the clusters. So these are the number of data points that belong to each feature. It's a symmetric function of the sizes of the features. It's a function of the number of features, which itself is a symmetric function of the sizes of the features. And it's a function of the number of data points. So this one's a little bit different. In clustering, the number of data points is the sum of the sizes of the clusters. So it's a symmetric function of the sizes of the clusters. And so implicitly, you can have an EPPF, and it can be a function of the number of data points. In feature modeling, that isn't the case anymore. I can have 10 data points and 0 features. I can have 100 data points and 0 features. These are all acceptable. And so we don't have this sort of strict tie anymore with the number of features and the number of data points. So let's say that, so we see that if we're going to have something like a partition probability function here, it's going to have to be a function of the number of data points and then a symmetric function of the sizes of the features. OK, so what have we done so far? Well, first of all, I'll note that this Indian buffet process is a valid exchangeable feature allocation. Remember, we added a Poisson number of features at each time. That's potentially unbounded, but it is finite. Also, we note that if I change the order of the data points, these sizes don't change. So it's exchangeable. And then we've also basically said, OK, let's define this as the exchangeable feature probability function. Then the Indian buffet process, the IBP, has an exchangeable feature probability function. But of course, the whole point here was to say, what can we say about all exchangeable feature allocations, not just some particular exchangeable feature allocation? So the real question is, does every exchangeable feature allocation have one of these EFPFs that we've just defined? And actually, the answer is no, and here's a simple example to tell you why not. So let's imagine this following counterexample. There are just 2 features this time. It's bounded at 2 features. And for each data point, I'm going to choose the assignment of the data point to the features IID independently and identically from the following distribution. So in particular, I have one feature and not the other with probability P1. I have both features with probability P3. I have neither feature with probability P4. And so if I had an EFPF, this exchangeable feature probability function that we just defined, then these 2 feature allocations would have to have the same probability. In the first one, we have 2 data points and 1 data point per feature. In the second one, we have 2 data points and 1 data point per feature. That's all that the EFPF depends on, so these would have to have the same probability. But we can calculate their probabilities. So this one is just the probability of the first row times the probability of the second row. That's P1, P2. This next one is the same thing, only in this case it's P3, P4. I can easily choose P1 through P4. You know, they just have to be numbers between 0 and 1 that add to 1, so I can easily choose them so that this inequality holds. And therefore, I cannot have an EFPF here. So let's call this example the 2-feature example, this case where I have this inequality. So what have we seen so far? Well, sort of historically, we know that if I have any exchangeable clustering, then it has to have a representation with an exchangeable partition probability function. But we've just seen that if we define this exchangeable feature probability function, it sort of comes up short. The Indian buffet process has one, but the 2-feature example, which is pretty simple, doesn't. So if we want to find, ostensibly this characterization of exchangeable feature allocations, then we have to go back to the drawing board and ask ourselves, what else do we know about exchangeable sequences of random variables? Sequences of random variables where if I permute some of the random variables, the distribution doesn't change. Well, it turns out that Di-Finetti's theorem tells us that if I have an exchangeable sequence of random variables, then there's always some Di-Finetti mixing measure such that if I make IID draws, independent identical draws conditioned on that measure, it has the same distribution as the original exchangeable sequence. Now, in general, this mixing measure could be something totally difficult to work with. It would be a really big pain and wouldn't actually be useful in practice, perhaps. But it turns out that for clustering, the Di-Finetti mixing measure is quite nice. And so we might think that we would find a nice one that we can maybe represent in some sort of nice way for feature allocations. So before I tell you exactly what the mixing measure is for clustering, let me tell you a way that you can generate an exchangeable clustering. So imagine that this is the unit interval from 0 to 1. The first thing that I'm going to do is I'm going to partition the unit interval. So what I've done here is I'll note, I've shown you this sort of partition of the unit interval that has 6 subintervals. Now, in general, this could be just a particular instantiation of some random partition. So it could be totally some random variable. 2, it doesn't have to have 6 subintervals. It could have any finite number of subintervals. It could have countably infinitely many subintervals. These are all fine. But suppose I put down such a partition. Now, for each data point, I'm going to put down a uniform random variable on this interval 0 to 1. So for the first data point, I draw a uniform random variable. That's this one right here. For the second data point, I draw another uniform random variable. And the way that I'm going to define my clustering is I'm going to say that if 2 of my uniform random variables fall into the same subinterval in this partition of the unit interval, then they belong to the same cluster. So 1 and 2 belong to the same cluster, 3 starts a new cluster, 4 starts a new cluster, 5 belongs with 3, etc. Now, if you think about it for a second, we can see that this generates an exchangeable clustering. If I just permuted any of 2 of these independent, identically distributed uniform random variables, I clearly don't change the distribution. Everybody's sharing this underlying partition. But what Kmeans showed in 1978 is that the converse is true. That if I have any exchangeable clustering, then I can always find such a potentially random partition and describe its distribution in the following way. Now, let me say something really quickly, that this partition, since it was discovered by Kmeans, is often known as the Kingman paint box. And the reason it's called a paint box is that you can think of each of these subintervals as having some color associated with it. And so when I put down my uniform random draws, they get colored with the color of the interval into which they fall. And then finally, I'll group together the data points that have the same color into a cluster. Now, from a generative model perspective, this actually could be interpreted as sort of parameters of the model. So you could think of the yellow color as actually being some parameter that tells you how to generate pictures of cats. In this toy example, the blue color might tell you how to generate pictures of dogs, et cetera. Now let me show you the exact same model, but just slightly differently. So what I've done here is I've just separated each of these partition subintervals onto a different level. And I'm still saying that I make these independent uniform random draws for each data point. And then I say that they belong to all the groups that they intersect. And since these subintervals were chosen to be mutually exclusive and exhaustive on the unit interval, each data point intersects one and only one group called a cluster. But then, of course, there's this very natural generalization when you see it this way. What if I have some arbitrary subset now for each group? Then we'll call this set of subsets the feature paint box instead of the Kingman paint box. And we'll say the same thing, that when I put down a uniform independent random draw for each data point, it will belong to all the groups, now features, that it intersects. So in particular, this first data point intersects two groups, so it belongs to two groups, these two features. The second data point happens to belong to no features, that's fine. The third data point shares a feature with the first data point, and so on. And again, we can see that this generates an exchangeable feature allocation, because suppose that you permute any of the two data points. That's just permuting two independent uniform random variables, and everything's still exchangeable, so that's fine. And in fact, what we're able to show is that the converse is true as well, that if you have an exchangeable feature allocation, then you have an underlying feature paint box that represents its distribution. OK, so this was sort of the goal. We knew that exchangeable cluster distributions could be represented with Kingman paint boxes. And now we know that exchangeable feature distributions can be represented with feature paint boxes. And so we can actually go back and ask the question, well, we know the IBP in the two-feature example must have feature paint boxes. What are they? And does it lend some insight into what's going on with this EFPF? So let's start with the two-feature example, because it's a lot easier. We know that for the feature paint box for the two-feature example, there has to be some region of size P1 where one feature occurs but not the other. There has to be some region of size P3 where both features occur, and some region of size P4 where neither feature occurs. Now, to get at the feature paint box for the Indian buffet process, we're going to have to appeal to a different result. OK, so Thibault and Jordan in 2007 showed an alternative way that you can generate a feature allocation, an exchangeable feature allocation, with the same distribution as the Indian buffet process. So let me tell you this alternative construction. It goes as follows. So we're going to go through each integer, 1, 2, 3, et cetera, and we're going to generate a Poisson number. Then what we're going to do, so it should be km minus 1 plus 1. What we're going to do is just generate a beta random variable for each 1, 2, 3, up to that Poisson number. And so here, gamma and theta are parameters of the model again. In fact, they're the same parameters as the IBP. But let me go over what this looks like. So each of these beta random variables is going to be some number between 0 and 1. So let's go to m equals 1. The first thing we're going to do is generate some Poisson number. And suppose for m equals 1, that Poisson number is 2. Then the next thing we're going to do is for each of 1 and 2, generate a beta random variable. So that happens to be, say, Q1 and Q2, these independent beta random variables. So now we'll go to m equals 2. It will generate a Poisson number. Maybe that number happens to be 1. We'll generate one beta random variable. That happens to be Q3. We'll go back, m equals 3. We'll happen to generate a Poisson number that maybe is equal to 3. We'll generate 3 beta random variables, and so on. Now, let me tell you something that is a couple of facts about this distribution that might not be obvious. So one, there will actually be, at the end of this sequence of steps, a countable infinity of these frequencies, these numbers between 0 and 1. Two, their sum across all of the frequencies will be almost surely finite. So finite with probability 1. OK, so we have a bunch of numbers between 0 and 1 now, but the whole point was to generate an exchangeable feature allocation, in fact, one that is the same as the Indian buffet process. So how do we get a feature allocation from these numbers between 0 and 1? Well, what we can do is we can use each of these as the probability of a feature. So for the first data point, we're going to go to Q1 and say that we'll have this feature with probability Q1. Independently, we'll have the next feature with probability Q2. Independently, we'll have the next feature with probability Q3, et cetera, until we filled in a feature allocation for that first data point. Now, independently and identically for the next data point, we'll assign the features for that data point. Independently and identically for the next data point, we'll assign the features, et cetera. Now, again, we can see that this is exchangeable because we're making these IID draws, these independent and identical draws conditional on this underlying probability. And 2, it's a feature allocation because the sum of these probabilities is finite. And so the total number of features for any particular data point will be finite. And it turns out, in fact, as I said before, that this has the same distribution as the Indian buffet process. So what does this tell us? You know, the whole point of going into this was to say, what is the feature paint box for the Indian buffet process? So what does this tell us about the feature paint box for the Indian buffet process? Well, it tells us the sizes of the feature subsets. So in particular, Q1 is the size of the feature subset for that feature, et cetera. And now if we want to nail down exactly what the feature paint box is for this model, we have to say how these feature subsets intersect. And so in particular, we know that, let's start off again with the unit interval, 0 to 1. We know that there's some event of size Q1 on which feature 1 occurs, and some event of size 1 minus Q1 on which feature 1 does not occur. Now, independently, we choose to have feature 2. And so there has to be some event of size Q1, Q2 on which feature 1 and feature 2 occur, and some event of size 1 minus Q1, Q2 on which feature 1 does not occur and feature 2 does occur. And then recursively, this happens for feature 3. There has to be on each combination of feature 1 and feature 2 some proportional event on which feature 3 occurs, and so on. Now, what's interesting about this feature paint box is I didn't say, oh, here's where we use the Poisson distribution, and here's the beta distributed this thing. I just said, hey, if we have this sequence of feature frequencies, then this is how we get the feature paint box. If we have this sequence of feature frequencies for which we draw each feature independently according to those probabilities. And so actually, this is sort of a more specific model where we have these frequencies and we can get the resulting paint box. And it's actually much sort of easier than a more general paint box. And so let's call this feature frequency models of this form, and ask ourselves, well, maybe this is a way to characterize exchangeable feature allocations, because it's a lot simpler. So it would be nicer if we could always characterize things this way. But of course, we go back to sort of our go-to counterexample. And the 2-feature example will tell us that, no, this is not a characterization of all exchangeable feature allocations. And so in particular, if it were, then it would have to be the case that the occurrence of feature 2 is proportional on the event that feature 1 occurs and feature 1 does not occur, the other way. And so if I choose P2 to be 0 and P3 to be non-0, then I don't have that proportionality. And so this is not a feature frequency model. And so at this point, we have this sort of interesting fact that the Indian buffet process has an EFPF representation, this feature probability function, but the 2-feature example does not. The Indian buffet process is a feature frequency model, but the 2-feature example is not. Maybe they're the same thing. And so to get at that question, there's sort of 2 directions. So if I have a feature frequency model, do I have an EFPF? And if I have an EFPF, do I have a feature frequency model? And so let's look at one direction. If I have a feature frequency model, do I have an EFPF? Well, we know how feature allocations, exchangeable feature allocations, are generated in feature frequency models. We make these independent Bernoulli draws across data points and IID draws, independent Bernoulli draws across features and IID draws across data points. And so we can calculate the probability of the resulting feature allocation. In particular, any one feature is a sequence of identical and independent Bernoulli draws. And so if the probability of this feature is Q1, then the probability of this whole feature, the assignments of the data points to features, is Q1 to the number of data points that belong to this feature times 1 minus Q1 to the number of data points that don't belong to this feature. Of course, this is true for any feature. And actually, remember, we don't know the order of the features, so this could have come from any of these frequencies. We can take a product over all of the features we see, but implicitly, there could be countably infinitely many we don't see because they haven't been drawn, and they were all unsuccessful Bernoulli draws. And then finally, we take an expectation because these Qs might be random. And so again, the question we want to ask is, does this have the form of an exchangeable feature probability function? In particular, it's a function of the sizes of the features. It's a symmetric function of the sizes of the features. It's a function of the number of features, which itself is a symmetric function of the sizes of the features. And it's a function of the number of data points, but that's fine. And so this can be expressed in exchangeable feature probability function form. And so we know that now, if I have a feature frequency model, then I must have an EFPF representation. What about the other direction? If I have an EFPF, do I have a feature frequency model? Well, in the interest of time, I'll just cut to the punchline and say, yes, in fact, I do. And so these are the same. So what is sort of the take-home message of this part of the talk? Well, if I have an exchangeable feature allocation, the whole point going in was to say, what can I do to characterize the class of all distributions over these exchangeable feature allocations? And in fact, we found such a characterization in the feature paintbox. And then it seemed like the EPPF from clustering this partition probability function was sort of coming up short. Well, you know, we can define an EFPF, this feature probability function, but, and it does contain the Indian buffet process, but it doesn't contain the two-feature example. But I think that's the wrong way to think about it. You know, this whole time we've had clustering over here and feature allocations over here, but really clustering is a particular case of feature allocations where each data point belongs to one and only one feature. And so really from that perspective, exchangeable clusters are analogous to models with EFPFs as characterizations of alternative correlation structure. And so really EPPFs are analogous to EFPFs. So what do I mean by that? Well, in general, if you tell me the sizes of the subsets in the feature paintbox, then I can't tell you what the feature paintbox looks like because they could intersect in pretty arbitrary ways. But if I tell you the sizes of the subsets in the feature paintbox and I tell you I have an EFPF, then you can tell me exactly what the feature paintbox looks like. It's a feature frequency model. If I tell you the sizes of the subsets in the feature paintbox and I tell you that I have an EPPF, then again, you can tell me what the feature paintbox is. It's a Kmeans paintbox. Here, conditional on the sizes of the subsets, I independently belong to each feature. Here, conditional on the sizes of the subsets, I belong to one and nothing else once I belong to that one. And then there are a number of remaining connections if you're familiar with this area. So one way that you can generate these feature frequencies is something called completely random measures. And the idea here is, so we've discussed with feature frequencies that you have these frequencies, and you independently belong to each feature conditional on the frequencies. And somehow completely random measures are like choosing the frequencies themselves independently, conditional on their sum being almost surely finite. There's a conception, and there's a normalized version of this in clustering, and the Chinese restaurant process, which you may or may not have heard of, is a particular case of this model that's analogous to the Indian buffet process. And finally, there's a conception of dust in both the EPPF and EFPF cases. And then finally, you know, we've talked about sort of this case of I have pictures, and I might have a picture of a cat or a dog or a mouse, and then I generalize that to maybe I have a picture of a cat and a dog, or a picture of a cat and a dog and a mouse, or no animals. But in fact, I can go a step further and say I have 5 cats and 3 dogs and 10 mice. And sort of more realistically, you know, I might be modeling words in a document, and I might want to say that I have 23 words from a subject about the arts, and I have 15 words from a subject about economics, and I have 52 words from a subject about sports. And so there's yet a further generalization in this sort of combinatorial world. And so if you're interested in this feature allocations, probability functions, and paintboxes equivalence, then check out this first paper. If you're interested in particularly the Indian buffet process model and the Chinese restaurant process model and how they have these different representations, then check out the second paper. And if you're interested in this idea of sort of multiple integer belonging, then we go over that in our combinatorial clustering paper. Now, at this point, we've talked about a bunch of different types of latent structure that you might have in data. You know, there's clustering, where each data point belongs to one and only one cluster. It's sort of very canonical. We're all familiar with it. But then we talked about this generalization, where each data point can potentially belong to multiple groups simultaneously, features. And then we talked about, you know, there are these further generalizations. We can have each data point belong in some positive integer way to multiple groups. We could, in fact, have multiple data sets that, for some reason, share cluster centers. You know, maybe multiple data sets that are text data sets, and we want them to share topics. And so, you know, in these cases, there are really a lot of different types of latent structure that we can find in data. And we want to ask ourselves, how do we learn this latent structure? And so, well, what have people done for the past 50 years? Well, if you look at sort of the most common algorithm in unsupervised learning for the past 50 years, it's Kmeans. Why is Kmeans so popular? Well, it's fast. It's easy to parallelize, which contributes to it being fast. And it's straightforward to use. There's sort of not too much that you need to do in order to sort of use it out of the box and run it on your data. Now, at least as it's formulated originally, it only works for the case of clustering, and in particular, a fixed number of clusters. And so you might ask yourselves, well, you know, we've talked about all of these other different types of latent structure in data that we might be interested in. What if I want to look at these other types of latent structure in data? What do I do to learn those? Now, one option that you have is a set of models from what's called non-parametric Bayes. And so the potential advantages of these models are, one, they're modular. So I can build up these general latent structures that I've talked about so far. In fact, I can build up other ones that are somehow combinations of these different latent structures. They're flexible. So, you know, if I imagine that I'm looking at, say, some set of books that people are buying on Amazon, and I want to use a feature model to describe potentially their latent interests in those books, well, it might be that as I see more and more people, I see more and more latent interests that I haven't seen before. And so there are cases where I actually want the number of sort of latent groups to grow as the size of the data grows. And so these models are flexible in that way. And because they're Bayesian models, they have a coherent treatment of uncertainty. Now, this is all sort of well and good, but you know, I might have just a huge amount of data, and I really, you know, can't take the time to formulate these models, and I certainly can't take the time to run them on my data. And so I sort of give up on them and say, well, at least I can run Kmeans. And so our perspective with this MAD Bayes framework that I'm about to tell you about is to take these Bayesian non-parametric ideas and use them to assist the optimization-based inference community in the following way, to come up with modular, flexible, non-parametric objectives and regularizers, where these words mean, you know, what I said on the previous page, the versions from the Bayesian non-parametric models. And if you really like taking a Bayesian approach, then you can think of this as potentially a way to initialize some sort of Bayesian procedure like a sampler. OK, so what is MAD Bayes? Well, let me first talk about an inspiration for using MAD Bayes. So consider a finite Gaussian mixture model. So what I mean by that is I have K clusters. And in each cluster, the data is distributed as a normal distribution around the cluster center. Then it's this sort of classical fact that if I take the steps of the EM algorithm to learn the assignments of data points to clusters and the cluster centers, and I take those steps as the variance in the Gaussian goes to 0, as I take a limit, then they become the steps of the Kmeans algorithm. OK, and so the idea of MAD Bayes is going to be a step away from any particular algorithm and look at models, which will hopefully be more robust in some sense. So we'll look at non-parametric Bayesian models, take a similar limit to the one I just described, and get Kmeans-like objective functions. And so let me talk about what I mean by these three sort of key terms, starting with Kmeans-like objective. So in Kmeans clustering, we're interested in a set of cluster centers, which are these small blocks here, and assignments of data points to clusters, which are the colors. And what we want to do is find one of these clusterings, this Kmeans clustering, such that we minimize the sum of square distances between data points and their cluster centers. So somehow, this is kind of a worse clustering because data points can be a little bit farther from their cluster centers, and this is a better clustering because data points are closer to their cluster centers. And just to be slightly more formal, what we're really doing is taking a sum over the square distances between data points and the centers to which they're assigned, and then this equation here that we're minimizing is exactly the Kmeans objective, and it defines the Kmeans problem. Now, there are various ways that you can go about minimizing this objective, but a particularly popular way, the one that is sort of used most in practice, is known as Lloyd's algorithm, or sometimes the Kmeans algorithm. And it just has two steps, which are the following. One, we assign the data points to clusters by saying, what is the nearest cluster center? And two, we update the cluster centers to be the mean of the data points assigned to that cluster. And then we just iterate these steps until nothing changes. Now, this algorithm is pretty popular for two immediately obvious reasons. One, this assignment of data points to clusters can be done entirely independently and in parallel. Nothing has to communicate. And two, there are just two steps. This is it. This is everything. You can go and program it up in 2 minutes, and you're done. OK, so we want to get a Kmeans-like objective and nice algorithms in the way that I've described, starting with a non-parametric Bayesian model. So just at a very high level, what I mean by non-parametric Bayes is the following. So instead of trying to find a point estimate of cluster centers and assignments of data points to clusters, a Bayesian model finds entire distributions over all of these quantities. And two, what I mean by non-parametric in this context, non-parametric Bayes, is that the number of parameters can grow as the size of the data grows. And so there are a number of these models, and we're going to try to take a limit of them to get these Kmeans-like objectives for all of these different types of latent structure we discussed. And so how does this limit work? I mean, how do I even get from learning an entire distribution over, say, assignments of data points to clusters and assignments of, and the cluster centers to a particular optimization problem? Well, the first thing that I have to do is actually get an optimization problem. And so one way that I can do that is the so-called maximum a posteriori, or MAP, estimate. Now, how this works is I say, OK, well, the thing that I get out of my Bayesian analysis is this distribution over the parameters given the data. Again, these assignments of data points to clusters and the cluster centers. And I can just take the parameters that maximize this distribution. And so now what I'm going to do is I'm going to take a limit of this particular objective function, which is just the posterior here, in particular a limit as the variance goes to 0, as in the inspiration, and we'll get out a Kmeans-like objective. And so let me start by talking about what happens on a high level, and then I'll go into a particular example. So on a high level, we can start with a Bayesian model that is a mixture of K-Gaussians, and we get out K-means as our K-means-like objective when we use this MAD Bayes. We can start with a Dirichlet process mixture, which allows us to model this non-parametric number of clusters, this growing number of clusters, and we get out this K-means-like objective for an unbounded number of clusters. We can start with a hierarchical Dirichlet process, which is a Bayesian non-parametrics model that allows us to have multiple data sets that share cluster centers, and we get out a K-means-like objective for just that type of latent structure. And we can start with a beta process, which for the purposes of this talk is exactly the same as the Indian buffet process that we talked about in the last part. So we can start with this Indian buffet process, take this MAD Bayes limit, and get out a K-means-like objective for learning features, the assignments of data points to multiple latent groups. OK, so how does this, let's look at this last one in a little bit more detail. Now remember, the first thing that we start with is the Bayesian approach, which gives us a distribution over parameters. So here our parameters are the assignments of data points to features and a set of parameters that describe the features themselves. So if this were clustering, we'd have the assignments of data points to clusters in a binary matrix with one and only one row, one and only one per row. And we'd have a set of cluster means, one per row, in this A matrix. And so here now we can have this multiple assignment to multiple features. And we have these feature parameters that describe the features. And so what comes out of the Bayesian nonparametric approach is a distribution over these quantities. And in fact, when we use an Indian buffet process, we get the following distribution. So again, it's a distribution over the assignments of data points to features and the feature parameters, which occur explicitly here. And also implicitly, the number of features is some random variable here, so it occurs. And then what we're going to do is take a limit as this variance goes to 0, and also take a limit as this prior concentration parameter goes to 0. And now the key point here is that you don't have to bother with this equation. What you do is you just take what happens when you take the limit. And so when I take the limit, this is what I get out. I get out the following BPmeans objective, where BP stands for the beta process that we started with. And it has just two parts. So one is this trace, or Frobenius norm, between the data points and the assignments of data points to features and the feature parameters. And so this would be exactly the Kmeans objective if Z represented a clustering, if each data point was assigned to one and only one cluster. And then we have a penalty. So this is the number of features times some constant lambda squared. And so this penalizes the number of features. And now what we can do is we can come up with a BPmeans algorithm that's much like the Kmeans algorithm for trying to minimize this. And it looks like the following. So again, we have essentially these two steps. One, instead of assigning data points to clusters, we assign them to features now. There's this sort of new step of considering creating a new feature. And finally, we have this update to the feature means. Now, if Z were a matrix for clustering, if each data point belonged to one and only one cluster, then this would be exactly the K-means update for the cluster means. And here it's the slight generalization to feature belonging. And now we can run this on some data. So there's this data set that Griffiths and Garamani created in their original Indian buffet process paper. So one challenge in unsupervised learning in general, we're trying to find this latent structure in data. But how are you able to say that we found sort of the correct latent structure? And so one nice thing about this data set is that at least you have some intuition about what should be going on. So in particular, each data point is a picture of a table with some objects on it. And so there's a very natural feature allocation interpretation. In particular, the features should be the objects, each of the objects that are on the table. And the allocation of a particular data point to features should be the table and each of the objects that occurs in that picture. And so we can run BPmeans. Well, I mean, that's sort of what you would think should come out. And in fact, we run BPmeans, and what we get is the features are exactly the objects, the pictures of the objects, and the table, which I haven't pictured here. And we can look at timing. Yes?
So but in these pictures, each object was always in exactly
It's always in exactly the same space. Yeah, again, I think what's really nice about this data set is sort of illustrating that you're getting something reasonable. But it is a toy data set. OK, so now we can run BPmeans or the Bayesian posterior Gibbs sampler from the Indian buffet process. If we run this Gibbs sampler for 1,000 Gibbs steps, which may or may not have converged, then this takes about 8.5 times 10 to the third seconds. And if we run BPmeans, it takes just 0.36 seconds. So we can run it. Both of these could potentially benefit from multiple restarts, but in this particular case, we still can have sort of multiple restarts in this massive speedup. And I'll note that at this point, we're doing everything sequentially. So we're not taking advantage of any parallelism in this timing comparison. Yes?
On your optimization?
Yeah, the lambda squared. So the point I'll make about that is, so there are a number of parameters in the IBP that we've seen already, right? And so there's the concentration parameter and so on. Now, the Indian buffet process makes some very specific assumptions about the number of features you have, just because of its distribution, and the sizes of the features. And so if you run the Indian buffet process on this data set, then you're basically, no matter how you choose the parameters, you're going to get 10 or more features. And while the assignments will be sort of reasonable, you will get sort of the wrong number of features. Whereas there is an assignment of the parameter for BPmeans such that you get not only the right features, but exactly the right assignments of data points to features. Now, choosing that penalty parameter in general is a hard problem. We think that it's potentially an advantage to go from an integer choice to a continuous choice. but it's certainly not sort of exactly obvious how you should choose it. OK, so we can do this. We can also look at another data set, which is a collection of axis-aligned faces. So here are 4 examples. And we can run BPmeans on these axis-aligned faces. And we get the following. So let me explain what's happening here. We get an average face. Now, what I've actually depicted here is the first feature plus the second feature. So you can see that the second feature adds long hair. And what I've depicted here is the third feature plus the first feature. So you can see that it sort of changes the facial structure and maybe makes it a bit darker. And now we can get each combination exhibited in our data set. So we can have a person that's just sort of the average face. We can get one with long hair, and one with long hair and the different facial structure. Now, this is sort of just a general exploratory data analysis problem. You know, in the previous case, clustering would be inappropriate. You would not get out the different items on the tabletop by using clustering. But here, you could run clustering, and you might ask yourself, well, the number of groups that we get by running this feature modeling ends up being 4. What if I just run Kmeans with 4 clusters? And so we can do that, but you get something different. In particular, this last cluster isn't sort of a combination of dark hair and or hair and darker skin color. It's just a different cluster. And now each data point belongs to one and only one cluster. So it's a different type of analysis. And then finally, as just a proof of concept, I'll say that we can take these algorithms and parallelize them in the following way. So it's just a tiny bit more complex than doing Kmeans, where Kmeans you just run all the assignments in parallel and there's nothing to think about. Here, there's the problem that you might be introducing new clusters or features. And so we take the approach of dividing our data set, sending it to processors, and then optimistically proceeding as though we can just add clusters or features, and then finally resolving conflicts at the master, and then sending out the data again and proceeding like that. And so when we do this, then just as, again, as a proof of concept, we can take the clustering version, 134 million data points for that, and it runs in about 5.5 minutes per iteration. And we can take 8 million data points for features, and it runs in about 4.3 minutes per iteration. But again, part of the point of this is just that you can get a new objective function for a different type of latent structure that you hadn't previously had by using this approach. And so again, that's the idea here, providing these new objectives and regularizers, and hopefully have these straightforward, fast algorithms like Kmeans. And so if you're interested in MAD Bayes, I'll direct you to our MAD Bayes paper. One of the reasons that it's called MAD Bayes is that it stands for map-based asymptotic derivations from Bayes. 2, check out our optimistic concurrency control paper for information about distributing these computations. And then finally, if you're really interested in staying in the Bayesian framework and actually learning a full posterior in some sort of large data context, then check out our streaming variational Bayes, where we look at those types of approximations. Thank you.
Great. We have time for a couple questions. Yes, good.
So going back to the first part of your talk,
Yeah.
right? What is gained from a practical point of view by your feature allocation process compared to something like the Indian buffet process?
Right. So, oh my. So I'm not proposing a new process. I'm looking at the entire landscape of possible processes. So I think that the point is a fewfold. So one is we found out that the EFPFs are equivalent to the feature frequency models. So one thing that's happened sort of historically in the clustering world is that what people will do is they'll take sort of a Chinese restaurant process and realize, oh, it's missing some characterization or some aspect that I'm interested in. So one classic example is power laws. So with the Chinese restaurant process, the number of clusters grows in expected value as log of the size of the data, and you might want that to actually be a power law for sort of physically realistic reasons. Now, what ends up happening is that by doing that, you generate a new EPPF. And so people look at different EPPFs that you could use. And so you might think the same thing in feature modeling. You might think, OK, I have an IBP. I'm going to change it in some way and get a new EFPF. And this tells you that if something you're interested in is dependence between the features, if you, for instance, in a toy example, you're not interested in independent cats or dogs in your pictures, but you're interested in modeling sort of cars and tires, and we want to find those as features, well, there's an implicational dependence there, right? If I have a car, then I want to have tires all the time, or pretty much all the time. And they're not chosen independently. And so this tells you that if you're really interested in modeling that type of structure, then you need to have something that does not have an EFPF representation. Whereas an EFPF is nice because it gives you sort of nice computational aspects. It might lead to sort of nice skip sampling algorithms and things like that. This tells you, no, you can't get out of that. And then besides that, right, no, it's not a constructive, here's a new model that you can look at. It's a map of the models that people look at. And I think that that's been useful in clustering, that people look at ways of using different EPPFs for different samplers. They look at ways of using the sort of underlying additional random variables that come from a Kingman Paintbox and samplers. And I think that there's no reason to think that that couldn't also be useful in the feature world. But no, it's not constructive.
So in the second part of the talk, I saw how you're taking the limit of these particular hyperparameters
Yeah.
in the model, and it seems like depending on what the latent variable model is, there's different ways to do that.
Right.
Are you proposing like a particular way of doing that for all latent variable models, or is there sort of an art to it?
Right. So all I've shown here is Gaussian likelihoods, and there you just take the Gaussian variance to 0. In general, there's this one-to-one correspondence between Bregman divergences and exponential family models, and that's basically what would happen in a general exponential family model. Now, what you do beyond exponential families, I don't immediately have intuition for what would happen there.
So the data mining community has proposed a wide range of generalizations of Kmeans.
Mm-hmm.
And if you look at this, what you call BPmeans, does that correspond to some of those generalizations?
So we're not aware of any generalization that it corresponds to. It certainly looks similar to things like Kmeans and factor analysis, but in this particular 0-1 model, we're not aware of anything that it corresponds to.
Okay.
Yes?
Marina?
Can you generalize math based to combinatorial clustering, counting features?
Right, we haven't tried that. I would think so. Yeah.
All right, let's thank the speaker again.